Hello everyone, welcome to the second lecture on the topic of flow measurement, which we are doing in this week number 9 of our MOOCs course on the principles of mechanical measurement. Now, in the previous lecture, we have discussed about, or I should say we have summarized the different methods of flow measurement into a few categories, and out of which we have discussed about the obstruction flow meters. Of course, before starting that, we discussed about a few fundamental concepts of fluid mechanics like the streamlines, path lines, streak lines, stream tubes, and then the development of the Bernoulli's equation, which is one of the very important equations from measurement point of view, particularly about the obstruction flow meters, which we have discussed in the previous lecture. Under obstruction flow meter, we have discussed about three different kinds of meters, namely the orifice flow meter or orifice meter, flow nozzles, and the venturi flow meter. Today, we shall be discussing a bit more on that, so that we shall be able to solve some numerical problems, and then we shall proceed to discuss about a few other devices. Just a quick recap on the obstruction meters. Here our objective is to decide or determine the flow through a pipe like this. Suppose we know that some liquid or gaseous fluid is flowing through a pipe in this particular direction, and we want to measure the flow through this pipe under say steady state condition. Let us choose one particular cross section. So, this is a section where we want to get a measure about the flow rate, that is Q dot as per our notation. Now, let us now break the pipe along this cross section or the selected cross section into two pipes like this. This is one of the pipe section and this is the remaining section of the pipe, and let us put couple of flanges, attach couple of flanges here. Now, instead of having a single pipe, we have broken the pipe into two sections and we have attached one flange to each of the sections. Then whatever may be your flow measuring device, that you have to incorporate into this particular portion, whether that is an orifice kind of flow meter or venturi meter, or maybe not an obstruction type at all, maybe some other kind of flow meter that will go into this crossed portion. So, if we are talking about say orifice flow meter, then between these two flanges, what we are going to incorporate is just a plate having same outer diameter as this original tube, something like this, and with a small orifice in between. Like this portion is solid, so that which is blocking the flow, and only the in between small circle is the one which is allowing the fluid to flow through. This is what we have in case of an orifice meter. Instead of a flow, in case of a flow nozzle, we select a pipe section having the same diameter as the original tube, which is again have flanged on either side. This particular flange will be coupled to this one, and this particular flange will be coupled to this one, and in between we have a nozzle kind of thing, a section of reducing cross section area. So, once we connect this one to the original channel, your flow section looks somewhat like this. So, the fluid on the, or I should not put this particular line that way. So, it is somewhat like this. So, fluid on the upstream side is able to flow through this way, and there is a smooth transition, smooth reduction in the cross section area on the upstream side, but that is not there in the downstream side. Whereas, in case of a venturi meter, we put a proper meter there, where we put a convergent divergent flow channel of something like this, where this particular portion is again attached to this particular flow flange, this flange is attached to this particular flange, and in between we have the throat, which is the smallest cross section area. So, this is what we have in case of a venturi meter. And we have discussed about the application of Bernoulli's equation to get a mathematical form, and just repeating from there, we have seen that the theoretical flow rate can be given as A2, where A2 refers to the cross section area at the location number 2, which is the second one of our selected location for pressure measurement, or you can also say this is a 2 refers to the location where we have the downstream pressure trap into 2 into delta P. Delta P is the pressure sensed by your differential pressure transducers divided by rho f for the fluid into 1 minus A2 square upon A1 square. A1 referring to the area corresponding to the first location of the pressure tapping. Quite often we use the symbol beta, particularly if you are dealing with a tube of circular cross section, then you use the symbol beta as as d2 upon d1, that is the diameter corresponding to the smaller cross section area divided by the diameter corresponding to the larger cross section area. Accordingly, a2 square upon a1 square can be written as beta to the power 4, and hence this particular relation becomes now, if we take everything out or the constant part out, actually it becomes a2 upon root over 1 minus beta to the power 4 into 2 delta p upon rho for the fluid whole to the power half, and this portion is a constant generally for a given venturi meter or given obstruction time flow meter. So, this can also be written as some k prime into 2 delta p upon rho f. Now, rho f depends upon which kind of fluid you are dealing with, and delta p will be the actual measurement that you are doing using your differential pressure transmitter, and then the actual flow rate will be the discharge coefficient times the theoretical flow rate. So, we have of course discussed about the relative merits and demerits of all these 3 obstruction meters, but let us summarize them to get a common features of all the obstruction meters. All the obstruction meters generally are low cost devices. Orifice meter is a particular one, or orifice meter is the one with very low cost. Generally venturi meter is more costlier compared to the other two, but still their costs are much lesser compared to other volume flow meters which we shall be discussing today. They are all simple in construction. Again, orifice meter is just a plate with a small orifice in between. Venturi meter is just a convergent divergent channel or convergent divergent nozzle, I can say. None of them are having any moving part, that is why their maintenance requirements are generally quite low, particularly for venturi meter and flow nozzle. However, orifice meter may require certain maintenance, particularly if we are dealing with some kind of fluid where there are solid suspensions, because those solid suspensions or darts may easily block the venturi, or I should say the throat, in case of an orifice meter. They can be dealt with a wide variety of working fluids. Generally they are restricted to liquids, but certain situations we can discuss or we can use them for gaseous flow measurement as well. There is option for selecting the range by varying the corresponding coefficients, by varying the area ratios, that is this beta. We can apply them for different ranges of flow rate or mass flow rate or velocities. They are easily available. There are hundreds of manufacturers or suppliers available to supply any of these meters, like a venturi meter or orifice meter. You can always purchase from market for the fluid that you are likely to work with and exactly for the flow range which you are likely to deal with. There are extensive experience and performance database, because people are using these meters for several decades, and more or less we know everything about them, what to expect from them. And accordingly we also have readily available standards, which are the standards to follow, what should be the installation procedure, what should be the calibration procedure, exactly how we should take the flow reading. You can always get lots of help about this. However, because of their simplistic nature, they also have several disadvantages. Like the biggest disadvantage is the flow rate is a nonlinear function of delta p, like the expression that we have derived in the last class, and I have just written here. Q dot actually the flow rate Q dot actually is proportional to delta p to the power half. Therefore, this is a nonlinear relation, and hence as the pressure drop keeps on increasing, delta p Q dot increases in square, that is Q dot square is proportional to delta p. So, for a given pressure drop, Q dot is or for a given amount of increase, I should say, suppose in one situation whatever pressure drop you are getting, in the second situation you are having double pressure drop, then corresponding increase in the flow rate will be 4 times. So, for a given range of pressure drop which your pressure drop measuring instrument can handle, there can be significantly larger range of flow rate that we may have to deal with. So, pressure transducer may require very large range to deal with a large flow rate variation. Then it is true for any kind of device, when you are talking about a large range of operation, then accuracy will always be affected at the lower ranges. So, they are not that much accurate when you are dealing with low flow rates. calculation is strongly dependent on the fluid properties, parameters like density and viscosity in particular. They are not at all suitable for compressible flow, because the equation that we are using, that we have derived using the Bernoulli's equation, which on the first assumption there was the incompressible flow. Of course, not today, but in the next lecture we shall briefly be discussing about the application of these obstruction meters in case of compressible flow, particularly for gases, means some sort of corrective measure that we can take, but that we shall be discussing in the next class. And they are generally used only for steady measurement. We hardly use venturimeters etc. for transient measurement, because again the application of Bernoulli's equation is generally more common in steady flow situation. And the biggest point that I would want you to make a note of is an intrusive measurement. Intrusive means we are putting some kind of device within the flow field, whether it is an orifice or whether it is a venturi kind of channel. We are changing the flow field configuration, or I should say we are changing the flow conduit configuration. That kind of situation is called an intrusive measurement, that is putting something into the flow field. And whenever you are putting some kind of device into the flow field, that is whenever you are doing some kind of intrusive measurement, there will be some amount of pressure loss. So, there will be significant amount of head loss. Of course, the amount of head loss, the magnitude of pressure loss will depend upon the device that you are using. Like we have discussed in the previous class, that venturimeter can have a quite high pressure recovery coefficient, that is on the downstream side it can recover about 90% of the initial pressure, but still there is a loss of 10%. Whereas in cases like flow nozzles or orifice meter, we can have significantly larger pressure loss, and that is true for any kind of intrusive measurement. We would like to go for non-intrusive measurements, where we are not at all going to put anything into the flow field, rather we shall be doing measurement only using some external parameters, like some examples we shall be seeing today. There we do not have any such kind of pressure loss. So, this pressure loss, or because of the intrusive nature of measurement, is one big concern with this kind of obstruction meters. Now, let us solve some numerical examples. Read out the problem carefully, what is given here. Here we are talking about a venturimeter which we are using to measure the flow rate of water at 27 degrees Celsius in a 20 millimeter diameter line. So, let us note down the information. Say capital D refers to the channel diameter, which is 20 millimeter, that is 0.2 meter. The venturi has a throat diameter of 10 millimeter. So, the smaller diameter is 10 millimeter, so 0.1 meter. That means your beta, the ratio of diameter small d upon capital D, is 0.5 in this case. It has been found that CD remains constant at 0.95 for a particular range of Reynolds number 10 to the power 4 to 10 to the power 6. Actually, the biggest concern about using this obstruction type device is the value of this CD. CD can vary with several things. CD can vary with the Reynolds number, the flow velocities can vary with the fluid property, and can vary significantly with this beta. So, we have to be very sure about which CD value to use during the calculation, because CD is the ratio, while ratio of theoretical, or I should say the actual to theoretical flow rates. While theoretical flow rate we can easily calculate, if we do not know the CD properly, then your actual flow rate calculation will be wrong. So, we generally depend upon some kind of experimental charts or certain experimental correlations or empirical relations to get the value of CD. And this particular venturimeter that we are dealing with here is found to have a constant value of CD of 0.95 only in this particular range of Reynolds number. So, the first thing that we have to find is the minimum flow rate that should be measured with this venturi. It is spelling is wrong, it should be venturi, this venturimeter. So, what we are trying to say here, that we would like to use this particular CD value of 0.95 because we do not know any other value of CD for this given venturimeter, but it is also said that this particular value we can use only when the Reynolds number is at least 10 to the power 4. Then what should be the smallest mass flow rate that we should measure with this? The smallest mass flow rate should be the one that gives us this particular Reynolds number, that is 10 to the power 4. Now, what is the value for Reynolds number or expression? We know that Reynolds number is rho into velocity into the channel diameter by viscosity. Now, property values we need, which I have not provided in this particular problem, but I have made a note of this particular properties. In this particular case, density we are going to take as 1000 kg per meter cube, and mu, that is viscosity for the fluid, that is water, we are going to take as 8.6 into 10 to the power 10 to the power -4 Pascal second or kg per meter second, which is the standard SI unit this. So, for a given value of Reynolds number 10 to the power 4, then this is the expression for this is the, we can calculate velocity from there, but our objective is not velocity, rather mass flow rate. Then how can we relate velocity with mass flow rate? We know that mass flow rate is equal to rho f into V into the flow area, that is rho f into V is m dot by area, that is 4 m dot by pi d square. If we put it back here now, rho f into V becomes 4 m dot by pi d square into, we are left with d upon mu f, that is 4 m dot by pi d into mu f, from where m dot is equal to pi d mu f upon 4 into the Reynolds number. Now, how we can calculate this one? What are the values given? We know the value of mu f, that is given, capital D, the diameter of the pipe is 20 millimeter, and Reynolds number. So, if we put Reynolds number equal to 10 to the power 4, which is the minimum workable value of Reynolds number, then we get the minimum possible mass flow rate. If we put the value, I pre-calculated the number as always, so it will come as 0.135 kg per second. Just put the numbers there, you will get this value. So, this is the smallest possible mass flow rate that we should deal with. If our interest in the volume flow rate, then we can also calculate the volume flow rate from there. Like what should be the minimum volume flow rate if we are looking to calculate Q dot mean? What is the relation between mass flow rate and volume flow rate? So, if we divide this mass flow rate m dot mean by density, you are going to get the volume flow rate in meter cube per second. So, you have the value now. Now, come to the second question. What pressure reading in millimeter of mercury would be experienced for this flow rate? Here, this pressure drop across this venturimeter is being measured by an U-tube manometer, and we can assume it to be an U-tube manometer, which is using mercury as the manometric fluid, and accordingly we have to calculate the pressure drop corresponding to this particular mass flow rate, this particular m dot, and actually not pressure drop, not delta P, you have to calculate the height of the manometric fluid column. If we draw it, then let us say this is your channel and this is your venturi portion. So, we are putting a mercury U-tube manometer, something like this, one on the upstream side and other on the downstream side, or I should say not downstream side, exactly at the throat location. So, this is your location 1, this is your location 2. Now, where pressure will be higher? At P1 will be higher or P2 will be higher? Definitely P1 will be higher because fluid is flowing from high pressure to low pressure. So, P1 is higher. Accordingly, the manometric fluid will may be showing a balance somewhat like this. So, if we see from there, this particular portion we are having a manometric fluid column of height h. Here we are suppose having only the working fluid, which is water, that column height of capital H. Then on the other arm, here we are having something left of height capital H minus small h of the same water. So, if we write a pressure balance along this particular dotted line now, then what we can write? On one side we can write P1 plus rho f g capital H, on the other side we can write P2 plus, we have a manometric fluid column of height small h. So, rho m, which is manometric fluid density, g into small h, plus rho f to g into capital H minus small h, because on top of the manometric fluid column we are having this particular water column, that is P1 minus P2 is equal to, so rho f g h cancels out, we are having rho m minus rho f into g h. So, if we take it back to the original expression for m dot actual. So, m dot actual will be equal to C D into rho f into A2 divided by root over 1 minus beta to the power 4 into 2 delta p by rho f whole to the power half, which we have just written in the previous slide. Now, what is your delta p? In this particular case, delta p is p1 minus p2, which is rho m minus rho f g into h. So, if we so here I have written C2 mistakenly, it should be CD. So, it should be CD into rho f A2 to power 1 minus beta to the power 4 into 2 g into rho m upon rho f minus 1 whole to the power half into square root of h, and we have to find the h corresponding to the m dot minimum, which is this value. Everything else is known. Here A2 will be equal to pi by 4 small d square, which is the area of the throat. So, if you put everything here, smallest value of h mean, which corresponds to the m dot mean, this particular one will be coming as 12.4 millimeter. So, this way we can calculate the smallest possible elevation in mercury column that we are going to get in this particular situation. And then the third part of the question is, what is the maximum measurable flow rate if the manometer has a maximum possible reading of 250 millimeter of mercury. So, in the third part you are given with, here your h is 250 millimeter. So, put the values, you are going to get m dot max in this particular case, and in this case m dot max is going to come as something like 0.6 kg per second approximately. Here of course, one information I am not given, that is the manometric fluid density rho m. Commonly we take that as 13,600 kg per meter cube for mercury. So, we have solved all the three. This is the first answer of the first part, this is for the second part, this is for the third part. But before we conclude, there is one final check that we have to do. While calculating this maximum mass flow rate, we have used the same CD value of 0.95. However, we have to check whether this is at all within that particular mentioned range of Reynolds number or not. So, if you calculate the Reynolds number corresponding to the maximum mass flow rate, your RE max will be something like 4.4 into 10 to the power 4. So, this is perfectly within the range. However, if this is coming greater than 10 to the power 6, then the value of CD equal to 0.95 is not applicable. So, you have to be careful in practical application. Another small problem, here we are dealing with another venturimeter where the dimensions are given in a different way, 200 mm by 100 mm. This is a quite standard way of representing. This actually means that 200 millimeter is the actual pipe diameter, 100 millimeter is the throat diameter. So, your beta is 100 millimeter by 200 millimeter, that is 0.5 in this case as well. And now you have to calculate the this venturimeter is measuring flow rate of oil of a density 780 kg per meter cube. Pressure difference is measured using an water manometer. So, here your working fluid density is 780 kg per meter cube, and manometric fluid density is that of water, that is 1000 kg per meter cube. And you have to calculate what is the ideal volume flow rate sensitivity. Sensitivity you definitely know, that refers to the change in output corresponding to the change in input. Now, for a venturimeter, what is your input and what is your output? Your input is the flow rate and output is the pressure drop, or actually you are measuring that in terms of the manometer. So, your output actually is the elevation in the corresponding manometric fluid column, that is H. So, if you write the expression earlier, you had an expression of Q dot is theoretical that we are talking about is equal to A2 in by root over 1 minus beta to the power 4 into root 2 g rho m upon rho f minus 1 into root h. This is what that we have just used, or if we write now root h by q dot, then what we are going to get? It is root over 1 minus beta to the power 4 by A2 into 2g, or I should write this way, 2g into rho m minus rho f minus 1 whole to the power minus half. This is the sensitivity. Of course, ideally you should have written at h by q dot, but as h by q dot does not have a direct linear relationship, so it is quite common to represent either as root h by q dot or h by q dot square. You can put the values, you are going to get the value of the ideal sensitivity, and if you are looking for actual sensitivity, then you have to multiply this one with CD. Fine. A third problem to finish up the thing, here we are having an orifice meter to deal with, an orifice meter with corner taps. This is important. We have discussed the location, that the location of taps strongly influences the corresponding pressure recovery part and the measurement, particularly the value of CD in practical situation. So, we are dealing with an orifice meter with corner taps. It is placed in a horizontal pipe of 200 millimeter diameter. The pipe carries water at 30 liter per second at 20 degrees Celsius. Throat diameter is 120 millimeter. So, we are having capital D equal to 200 millimeter, small d equal to 120 millimeter. So, beta equal to 120 by 200, that is 0.6 in this particular situation. Now, fluid properties are required, rho f, and it is given at 20 degrees Celsius. So, let us continue the same value of rho f, that is 1000 kg per meter cube. So, what is the mass flow rate? M dot volume flow rate is given, that is your volume flow rate is given as your q dot at 30 liter per second into rho f will be the mass flow rate. So, and if our interest is to calculate the velocity of the fluid, then how much will be the velocity? The velocity will be this volume flow rate divided by the cross section area, let us say the pipe area, that is q dot divided by pi by 4 d square. So, you can calculate the velocity, the value will be coming something like 0.9548 meter per second. From there you can calculate the Reynolds number. So, Reynolds number will be rho v into d by mu. The density and viscosity of water which we have used in the previous slide, the same we can use here, and the value will be coming something like 1.9 into 10 to the power 5 in this case. Now, the issue is that to calculate the pressure drop, we have to calculate the delta P in this particular problem. We know the mathematical relation. We know the mathematical relation as something like your q dot actual is equal to C D into A2 divided by root over 1 minus beta to the power 4 into 2 delta P by rho f whole to the power half. Here beta is given, A2 is half of pi small d square, A2 is pi by 4 small d square, and rho f is, we are using 1000 kg per meter cube, but what is CD? CD is the one that we have to know. So, for that purpose we need to use some kind of knowledge from previous experience, and this is one correlation that we are going to use here, where CD is generally found to be a function of beta, and there are some terms capital X and capital Y. If we expand them, they will be coming as functions of Reynolds number. So, if you use this, then your CD, just put the value of beta and Reynolds number in this expression, and your CD will be coming as 0.6084, which is quite common for orifice meters. So, if you put these values, then put all the solution, delta P will be coming something like 8.26 kilopascal. So, this is an example of how to use different correlations to get the value of CD. One thing you have to be careful here, the volume flow is given in 30 liter per second, that is your q dot is actually 30 into 10 to the power minus 3 meter cube per second. You should convert this one to SI unit before moving forward. So, with this knowledge of orifice meters and venturimeters and their application to real life problems, let us move on to a few more discussions. And for that we have another obstruction meter to deal with, but it is a different kind, something known as a variable area meter. Here the fluid is allowed to flow through, again between the two flanges we are putting the meter, but the meter is having a variable cross section area, not like the Venturi meter, rather it is uniformly varying. It is a taper tube through which the cross section area continuously increases in the upward direction, and generally fluid is allowed to flow only in the upward direction. As the fluid is flowing in the upward direction, the area is increasing. And inside this channel we have this float. This is made of different kinds of materials. Your float can be of different material, like that it can be of metal, stainless steel, titanium, aluminum, nickel, or we can use Teflon, we can use hard rubber, we can use PVC. There are several kinds of material used to make this float depending on what kind of fluid you are dealing with. As the fluid is flowing through this, the float will move upward and then will acquire an equilibrium position depending on the balance between the forces that is acting on this. I shall be coming back to this shortly, but the float can have different kinds of designs. The idea being we have to maintain a force balance so that the float is able to maintain a perfect equilibrium position. Then the accordingly whatever objective that we are going to look for, we can have different kinds of floats. Like we can have just ball float. Plain ball float is the simplest possible design, generally used in smaller units. The viscosity immune float, the second one, this is the one that is generally used when the viscosity of the fluid is very critical. The fluid that we are using, the viscosity can be quite critical. In that situation we use this viscosity immune float. I do not want to go to the details of their design, you can refer to the website which is shown here for more details on them. The viscosity dependent float, where actually you want to take the viscosity of the fluid into consideration, then we go for this. These two can be thought to be opposite to each other. One takes viscosity out of the equation, the other takes viscosity into the equation. This one is more suitable when you are dealing with large diameter tubes, whereas this one is used for small diameter tubes. This is the one that is generally used when we do not want large pressure drop. Of course, as the fluid has to flow past the float within this tube, there will be certain pressure drop. When you do not want any pressure drop or significant pressure drop, then we go for this. So, this the fourth one is particularly suitable when you are dealing with low pressure gas flows, when we can't afford too much loss of pressure. Now, have you seen this particular instrument? It is actually more popular by another name. That is why I am asking you. This is more popularly called rotameter. Rotameter is very commonly used. You may have already found rotameters in your university libraries or not libraries, university laboratories, wherever you have done some fluid flow related experiments or maybe heat transfer related experiments. This is called a rotameter, which is nothing but another obstruction type meter, traditionally known as the variable area meter. It has several advantages, like it can serve a wide range of operation. It has a very linear scale. The position of the float generally varies linearly with q dot, the flow rate, which is a big development over the previous ones, because in the previous case we had q dot proportional to root h, whereas in this case q dot is directly proportional to h. So, it is a big development or big advantage compared to the Venturi meters and orifice meters. There is a fixed pressure loss for any flow rate, generally as the pressure drop that the fluid suffers does not depend on the flow velocities. We can have them in easy sizes. We can also, suppose we are using one rotameter for a particular situation. Now, you want to change the range of operation, then we can easily do this just by changing the float itself. They are very easy to install. Just like in this diagram, the flanges are shown, which like in this particular case they generally are having some kind of threads. They can easily be tightened to the corresponding threads on the main pipeline, and we can start using this immediately. Hardly any calibration required, because they always come pre-calibrated, and we do not have to go for frequent calibration. Very low maintenance requirement as well. They are reasonably cheap, simple, can handle corrosive fluids as well, and they are generally highly accurate, particularly for low flow rates. Another big advantage over Venturi meters, they are very accurate or particularly accurate at low flow rates. But their disadvantage can be the accuracy is much lesser compared to venturimeters if we consider the overall range or the entire range, particularly at higher flow rates they are much lesser accurate. Calibration depends on temperature. I have just mentioned they are easy to calibrate or hardly requires any calibration, but that is true when you are dealing with an isothermal flow situation. When the temperature changes, fluid properties changes drastically, accordingly we may have to recalibrate them. Calibration depends on fluid properties. We shall shortly be seeing these 2 points in the next slide. They can be used only in vertical orientation, like orifice meter can be used only in horizontal orientation, they can be used only in vertical orientation. However, venturimeter can be used in any possible orientations. Solid suspension is not allowed, because as the float is there, fluid has to find a way past the float, and if there is some kind of solid suspension, that may not be able to pass through the small annular gap, rather that will block the flow. So, solid suspensions are not allowed, and because there can be possible wear and tear of the float itself, particularly when there is some kind of dirty fluids to deal with. And if we are dealing with a fluid which is not opaque, which is not, or rather I should say which is not transparent, the float will not be visible, and if we can't see the float, then we can't get the reading also, because as the float keeps on moving up and down, we generally have a scale on this particular glass tube, and when the fluid settles down at some position, say somewhere here, we can directly get the corresponding value from the scale, but if we are not able to visualize the float, we can't get the reading also. So, we can't use them for opaque fluids, and they can be expensive for large diameter applications. However, for smaller diameters they are very good to use, and they are not at all suitable for high pressure temperature applications. Generally we use glass tubes when you are working up to something like 200 degrees Celsius and just about 2 or 3 megapascal pressure. If we want to use for slightly higher pressure, then we can go for stainless steel tubes, which can sustain up to something like 300 degrees Celsius or about 70 megapascal pressure, but not very common to use that at such pressure temperature ranges. Now, let us just take a look what are the forces that is acting on the float. The float, there we can see there are 3 forces. One is the gravity which is acting downwards, one is the buoyancy force, depending upon the density difference between the flowing fluid and the float material, we can have a buoyancy force, and also as the fluid is flowing in the upward direction, it will there will be some kind of drag force which is also working in the upward direction. So, when the float acquires some kind of equilibrium position, then the summation of forces acting in, let us say this is a y direction, that has to be equal to 0. Now, what are the forces acting in this direction? Let us say this is the positive y direction. So, we are having the buoyancy force A plus the fluid flow force S minus the gravity W, that is equal to 0. Now, how much is the weight? Weight will be equal to rho B refers to the density of the float material into gravity into the volume of the float. Similarly, how much will be the buoyancy force? Buoyancy will be equal to the weight of the fluid that has been displaced by the float. So, it is equal to rho F refers to the density of the fluid, to G into VB. And what about this S? S is the drag force. Now, it will refer to the shear stress into the area of the float. And how we can get the shear stress? Shear stress can be certain constant K times half rho V square, where V is the velocity of the fluid, and of course rho F. So, if we put all these forces together now, then we can write that rho F minus rho B into G V B plus K A into half rho F V square is equal to 0, or A B I should say, K A B rho F into V square is equal to rho B minus rho F 2 into this to G into V B, or V square is equal to 2G by K into the area of the float. Here A B of course refers to the circumferential area or the peripheral area over which the shear stress is acting, into rho B upon rho F minus 1. That means if our interest is the flow rate, what should be the flow rate? Flow rate should be the AN, that is the area of the annulus, like this particular annulus through which the fluid is flowing. So, how much is the area of the annulus? A annulus can be written as pi by 4 into the channel diameter. So, channel diameter can be d plus by whole square minus the float area, where small d is the area of the diameter of the float. So, this is your small d, capital D is the smallest possible diameter of the channel, and y is the distance that has been travelled by the float when it has reached from capital D position to the equilibrium position, and b is certain suitable linear constant. So, d plus by refers to the change in the diameter as it is moving in the upward direction. So, d plus by is the effective diameter of the channel at this equilibrium position, small d is the diameter of the float. So, we have the area of this channel. We may have certain kind of coefficient of discharge also coming in. So, finally, if we put everything together, so we have ANN into CD prime into root over 2g by KAB into root over rho b upon rho f minus 1, that is certain discharge coefficient CD into a area of this annular portion into rho b upon rho f minus 1 whole to the power half. So, this constant CD, which actually takes care of all these terms, generally is a generally comes from the manufacturer, and what we do, we make the combination of these parameters capital D, small d and b such that this displacement becomes a linear function, or I should say q dot becomes a linear function of y. Then only from the scale directly we can get the measurement of the flow rate. So, variable area meter or rotameters are very common devices for fluid flow measurement, and this is a very simple way of getting their working principle. Another device, another obstruction kind of device known as laminar flow meter, they are generally used for high velocity fluids or for turbulent flow situation. In case of turbulent flow, actually this particular laminar flow meter is also known as target flow meter. So, this is another alternate name that is also very popular. Here what we are doing, here in the main flow stream we are putting this particular section. In this sections there are several small capillary tubes or very small diameter tubes, and we are allowing the fluid to flow through the small diameter tubes. As the fluid is flowing through the small diameter tubes, then or I should say the total fluid which is flowing through the entire cross section, that gets divided into several components, and as the diameter of each of these small tubes are so small, then each of them experience laminar flow, and we then make use of this laminar flow situation. How can we make use of the laminar flow situation? Sorry, I have made a mistake actually. This target flow meter term we shall be using later on. This is not suitable for laminar flow meters. I am very sorry for this. But let us come to this situation. For laminar flow meter, let us say this 1 and 2 are the cross sections. 1 is before it enters the laminar flow channels, 2 before once it exits the laminar flow channels. If we apply Bernoulli's equation, then P1 by rho plus V1 square by 2 is equal to P2 by rho, there is no change in elevation, V2 square by 2 plus G into HL, where G into HL refers to the loss in head because of this. Now, 1 and 2 are having same cross section areas. So, under steady state condition V1 and V2 are equal to this. That means, HL is equal to P1 minus P2 by rho G. Now, HL is coming because of the loss of the fluid, head loss of the fluid when it is flowing through this small dimension channel or small diameter channels, and as their diameters are so small that they can easily be visualized to be laminar flow. And for laminar flow, we actually have a measure of this HL. Have you heard about the Darcy-Weisbach equation? I am sure you have learned this in fluid mechanics, where for laminar flow situation, that is when Reynolds number is less than 2000, we can write this HL to be equal to F into L by D half rho V square. and this F for laminar flow is equal to 64 by Re, that is the Reynolds number. So, if we put this into equation, then if you put everything back here, the Q dot will be coming. I am not showing the development because you can just put this expression for HL into the equation, and this is also very standard. You will find this as 120 pi d to the power 4 120 mu f into delta p upon L, where L refers to the length of this portion, d is the diameter of the main tube, mu f is the fluid viscosity, and delta p is the pressure drop between portion 1 and 2. So, from the measurement of this pressure drop delta p, we can easily get this delta q. This equation is known as the Darcy-Weisbach equation, and we can easily get the measure of the flow rate using this. So, they are very easy configuration, particularly suitable for low flow rates and highly viscous fluids also. Again, high viscosity helps in laminar flow, maintaining the laminar flow situation. The Q dot, that is flow rate, is a linear function of delta p, just like the previous situation. They are direction sensitive, because in which direction flow rate is happening, accordingly the pressure drop direction will also change. So, we can also get an idea about it is flowing from 1 to 2 or 2 to 1. They have relatively wide range of flow rates as well, and very low noises measurement, because as we are dealing with laminar flow during measurement, hardly any disturbance in the flow stream. However, problem is they are restricted to clean flows, just like orifices. As we are dealing with small diameter channels, there can be blockage if there is any dart present in the flow stream. Then there can be maintenance issues, temperature compensation may well be required, because viscosity can vary significantly with temperature. So, we have to be careful about the flow temperature or the temperature at which you are doing the experiment. But laminar flow meter can be a good one to use, particularly when you are dealing with highly turbulent flows. Another one, often known as the drag force flow meter, or where I made the mistake, the target flow meter, that is a quite interesting example, not very popular. I should make it clear from the beginning, and also there are doubts whether we should call them obstruction meter at all. But what we have here in this drag force flow meter or target flow meter, we have a tube, just like shown here. We have a hollow cylindrical tube. Inside the tube, we have the tip of this tube is immersed into the flow stream, where we want to get the measurement of the flow. As the fluid is flowing over this, it experiences certain kind of force on this, certain kind of drag force, and that force is sensed by this pair of strain gauges, which are mounted on the inner surface, on the opposite inner surface of this particular cylindrical tube. And this force can be seen to be directly proportional to the flow. Like this is the situation, your flow plate, this particular head of this can be I should say the tip of this cylindrical pin can be like a flat plate, which is shown here. If it is a flat plate, then it will be oriented exactly perpendicular to the flow direction. Or we can also deal with spheres, if like instead of a plate, like it is shown a plate, but we can also have a spheres. And depending upon which configuration we have, additional circuitry located inside the cylindrical hollow pin takes care of the corresponding calculation. Now, when fluid is flowing over this, corresponding drag force can be seen to be CD into area of this obstacle into half rho f into v square. The value of CD, if we are dealing with a flat plate, CD is something like 1.28 approximately, I should say, it is 1.28. However, if we are dealing with a sphere, then CD can have a very wide range, 0.05 to 0.7. This is significantly wide range that we may have. So, and that depends upon the Reynolds number of the flow. So, we can have some kind of correlation to calculate CD based upon the Reynolds number, and once we know the value of CD, we can get the value of the velocity from this particular calculation. The big advantage is they can be used for gaseous situation as well. Both liquid and high velocity gas flows can be measured, or the flow rate I should say. They can be used for very critical applications like cryogenic applications, very high temperature pressure steams. We can also use them for dirty fluids, corrosive environments. They have excellent dynamic response, all the devices that we have used earlier. they are generally used for steady state response, but this is the one that has an excellent dynamic response, and so we can usually use them for dynamic measurement. They are suitable for sporadic or multidirectional flows as well. Low initial cost is quite initial setup cost is quite low, but because we hardly need anything, there is only a flat plate or a sphere and the corresponding circuitry located inside this hollow tube, that is all. The range of flow rate or the fluid to deal with, that can easily be altered just by changing the target or that flat plate. So, we can use the same meter can be used for different kinds of situations just by changing the tip of this, and there is no moving part. So, there is relatively very long life compared to a few other devices. However, calibration to be verified for every flow field, because calibration can be quite tricky, particularly the value of CD, which is dependent on the velocity itself. They are limited applicability in corrosive environment. I have mentioned earlier they can be used for corrosive situation, but generally when we are dealing with fluids with solid suspension or limited amount of solid suspension. But if it is highly corrosive, then that can corrode the plate itself or the tip itself. So, you have to be careful in such situations, and there is definitely large pressure drop which is going to happen across this. So, this is also certain kind of obstruction that is putting into the target, but they are not very popular. Rather, a device which can be visualized to be an improved version of this one is quite common in industries, which is called turbine flow meter, and this is no more an obstruction flow meter, this is a volume flow meter, the other category that we are going to deal with. Here actually we have a turbine mounted in the flow field. I shall briefly be going through them just to mentioning their operating principle. Here we have a turbine, these are the turbine blades. As the fluid is flowing through this, it strikes the turbine blades, therefore, the blade starts to rotate, and as the blade or the rotor starts to rotate, there is a permanent magnet mounted on the housing of this, and as the permanent magnet starts to move along with the rotor, then there is, whenever it crosses the pole of the coil, there is a change in the permeability, and that change in permeability can be sensed by any suitable instrument, and that can give you an idea about the flow velocity and correspondingly the volume flow rate of the flow stream which we are going to deal with. Generally, it has been found that the flow rate can be represented as F by K, where F is the means, as I have mentioned, there is a, whenever it crosses the pole, there is a change in permeability, and each such change in permeability gives leads to one voltage pulse. So, here F refers to the frequency of that voltage pulse and K is some instrument based constant. So, we can easily get the flow rate from this. They are highly accurate instrument, probably the most accurate one among all the ones that we are going to deal with or we are going to talk about. Their accuracy can well be in the range of, I should say, plus minus 0.5% or even lesser, particularly when dealing with liquids. For gases it can be slightly higher, but for liquids we can even go to 0.2%, and commercially available turbine flow meters generally comes with very good range of calibration and high accuracy. As I mentioned, they are extremely accurate and reliable over the entire range of operation, suitable for high pressure and temperature, suitable for both liquids and gases, wide range of operation. Their cost is low to medium, because I should say they are much costlier compared to the obstruction meters, but can be less costly compared to the next one that we are going to talk about, and they are excellent particularly when dealing with steady flow situation, but not that good in transient situation, because the frequency itself will become difficult to measure. They are limited to low viscosity fluids. For higher viscosity ranges, the drag force can become significant and can significantly affect, or I should say significantly dampen the rotational motion. There is rotating part, so there will be much larger wear and tear, much larger maintenance requirement. Turbine generally needs to be manually lubricated also to reduce this wear and tear. They can induce significantly large pressure drop in the flow stream, much larger compared to venturimeters, etc. Traditionally suited for unidirectional flow, because the motion of the rotor is insensitive to the flow direction, and so it is not possible to capture the flow direction using the turbine flow meter. They requires clean field, clean flow stream, because if there is solid suspension, that can strike the turbine blades, causing permanent erosion to the turbine blades and some clogging also. They are less accurate for unsteady flows and also for low flow rates. They are extremely high accuracy at the upper side of the range, but not that great on the lower side. But the next one can be extremely accurate over the entire range from 0 flow to very high flow rate, which is the electromagnetic flow meter. Working principle is very simple. You must have heard about the Faraday's law of induction, which is the principle of electric current generation, or I should say AC current generation, alternating current generation. That is, when a conductor is moving inside a magnetic field, then that produces an EMF, and if we capture that EMF, then we get electricity. That is the principle here. Here we have the any conducting fluid when that is flowing through a channel, we put a permanent magnet field or around the channel. Basically, if this is your channel, in between, if this is the channel, in between we are going to put the flow meter, and the flow meter will house a permanent magnet. And as the conducting fluid is flowing through this, because of the motion of a conductor in this magnetic field, there will be a current generation, which is given by this very famous the right hand rule, where if we put these three fingers perpendicular to each other, then the magnetic field will always be given, direction of magnetic field is given by this, and the flow velocity will always be given by this. Then this one, your index finger, will give you the direction of the EMF generation. From where we can get the idea about the direction of flow as well. Only one restriction is that this is a very simple working principle and extremely accurate. We hardly need to go for any calculation. There are several standards electromagnetic flow meters available in the market as well. But only problem for them is that the fluid has to be conductive. Conductive means it does not need very high conductivity. Common tap water itself has sufficient conductivity to deal with such flow situations or such kind of magnetic flow measurement, but they are not that much suitable for gaseous flow measurement. So, their advantage is highly accurate over the entire range, as I have mentioned, starting from 0 flow to the maximum flow suitable for this magnetic flow meter, insensitive to pressure and temperature, insensitive to fluid properties, because they are only sensing the EMF that is generated, and that is independent of the any property of the fluid. And very important, non-intrusive measurement. Whatever measurement that we are talking about, all are intrusive, but here we are not putting anything inside the flow field. Whatever we are doing, that is only outside. These magnets are only part of the wall of the conduit that you are dealing with. So, nothing is going inside the flow field, no pressure drop. So, this is a non-intrusive measurement. Suitable for liquids, solid and gas contaminants, because there is nothing to block the flow. So, we do not care about contaminants, and no pressure loss. But problem is the fluid needs to have some electrical conductivity. So, certain liquids and gases can't be used with this measurement. Complicated post processing circuitry, because the corresponding EMF needs to be related to the velocity or flow rate. A straight pipe section is necessary to allow the fluid to flow through the flow meter. For 0 flow situations, there can be certain drift created by the eddy current losses. However, generally that is taken care of the process by the processing circuitry, and they are costlier. They are more costlier compared to the turbine flow meters. But they are when we are not sure about the flow velocities to deal with, this is generally a very potent option to go for. So, that takes us toward the end of today's discussion. A few other volume flow meters I have to discuss, but I shall be discussing only in the next lecture, where I shall also be talking about mass flow meters. So, we have talked about the variable area flow meters and laminar flow meters today. Then we talked about the target flow meter, and then two different kinds of volume flow meters, that is the turbine flow meter and electromagnetic flow meter we have talked about. In the next class, we shall be starting with the discussion on ultrasonic and vortex shading flow meters. Then we shall be talking about the mass flow meters, where we directly get the measurement of the mass flow, like the Coriolis mass flow meter, and then certain kind of velocity based probes that we shall be talking about. So, till then I would like to take a leave from you. Thank you very much for your attention.